our thoughts surrounding electric vertical propulsion aircraft. There's two major reasons that people and our customers are excited about electric vertical takeoff and landing. The first is cost reductions. And in order to achieve a sustainable electric future in aviation, we have to address the cost reduction area. And most people think about the fuel reduction because of the elimination of diesel fuels and Jet A and gasoline. But one thing we're finding is that operators really care about the maintenance and the service intervals, the reduction of maintenance and the extension of service intervals. And these are almost as important as the elimination of fuels. Couple that with the operational flexibility of point-to-point aircraft, and we are able to not only enable their financial teams to have an exciting tool to use to reduce cost and provide more services, but the operational teams at our customers to also enable entirely new routes for aviation. So the way we think about electric vertical takeoff and landing aircraft is really in four parts. There's of course the aircraft that everybody thinks about. But coupled with the aircraft, and almost as important as some of the speakers were alluding to a few minutes ago, is the recharging system. So the charging system itself has to be deployed at multiple nodes to create a network well in advance of when the aircraft is deployed. And then of course, to get to higher and higher densities of aircraft in the sky on the network of deployed recharging systems, we have to have enterprise operation systems that allow the aircraft to commingle with each other and traditional air traffic in a highly optimized way. And in the near future, we have pilots in the plane. In the future, beyond that, we have autonomy. So near term, the training, and longer term, the systems that enable these aircraft to deconflict with cooperative targets and uncooperative targets in the sky. So this is a real photograph taken of our 7,000-pound aircraft from above it. It has a 50-foot wing. It's about 44 feet from the front to the back, and it's 14 feet tall. There's 1.3 megawatts of installed power on the four top lifting rotors, and there's about 400 kilowatts installed at the pusher. When it's cruising, the way that it operates is these four rotors turn on, lift the aircraft off the ground, and then the pusher rotor turns on and pushes the aircraft forward through the air. During that cruise phase, it's using about 100 kilowatts, and during that liftoff phase, it's using about 800 kilowatts. So there's control margin and significant climb margin built into the aircraft. The aircraft is designed around range because our cargo customers, UPS, FedEx, Amazon, DHL, the folks that move a lot of cargo, need an aircraft that moves a long distance. And the limit of technology today with batteries, motors, inverters, so the energy storage, the conversion efficiency of those batteries, the empty weight fraction of the aircraft, the structure and all the pieces of it, and the lift over drag ratio that we can achieve, all define the limits aerodynamically and energy-wise to achieve a 250 nautical mile aircraft. The peak speed is about 145 miles an hour. And when we take a couple batteries, so on a normal day, you can carry about 600 pounds of payload. When we take the batteries and we reduce the number of batteries we're carrying that are in the belly, you can get 1,500 pounds of payload. So we have both a cargo system and a passenger system. The passenger system has 6 seats. This is what the aircraft looks like from the front. These top rotors here are about 4 meters in diameter, and those independently modulate their torque to stabilize the aircraft just like your traditional quad rotor. But what's most interesting about this design is that within each of these motors, there's 4 independent motors for reliability and redundancy. In the back, there are 2 independent motors. All of the batteries are in the belly of the aircraft here. And you see these 5 ports here that are quick releases to drop the battery out of the aircraft. In a cargo mission, it was really important for our customers to put a lot of cargo into the airplane. So the fuselage is designed to handle 3 standard cargo pallets of goods in the aircraft, and the flat floor enables the customers to put the cargo in and move it around in a very logical and high-density way. What we're finding with customers is that they run out of volume before they run out of mass. So with 200 cubic feet of interior volume and an average package density between, say, 3.5 and 6 pounds per cubic foot, they'll only achieve 1,200 pounds of cargo in the aircraft. Fortunately, with a large cargo aircraft, it's also very easy to incorporate seats for passenger missions. So these CAD drawings show how those seats fit inside the aircraft for simplicity. There's a pilot seat in the front, and there's 5 passengers. The passenger up front may or may not want to have a screen in front of them. So there's significant leg room and comfort. This is what the aircraft looks like prior to a particular test flights. And we test fly the aircraft both in vertical mode and in horizontal mode. We anticipate achieving FAA certification and then other governing body certifications in 2024 to deploy this thing for both passenger and cargo missions. So this is myself in preparation for a test flight. We've flown hundreds of test flights in this vehicle. In 2018, we flew 150 test flights in a prior vehicle that had 8 rotors, and we've moved on to this vehicle, which has a longer distance range. So different test flights are done either in vertical mode. In this particular one, we have tethers to the ground for safety at a large airport, and in horizontal mode, where we temporarily put wheels on the aircraft to explore the test flying with the wing on it. We recently completed our phase 1 experimental flight test with populated islands to achieve the ability to fly over an urban environment. The view from the cockpit is absolutely wonderful. Without any type of propeller on the front, there's all glass in the front, and it's incredibly quiet. The electric motor makes a slight hum in the back of the plane, and the 3-bladed propeller, being 30 feet behind the pilot and pushing aft, makes very, very little noise. So the experience for passengers and pilots is completely different than you would ever get in a turboprop or a piston aircraft, and it's much like a glider. This is over the water, and I like this picture because it nicely shows the control systems. There are 10 independent control surfaces, so this horizontal stabilizer has 4 independent control surfaces. The ailerons are split into 2 per wing. You can see the lines down here. And that allows for aerodynamic redundancy. And each of these surfaces are powered by different power supplies and control lines so that the probability of failure is exceptionally low. Back to the recharging system, and this is a rendering of a recharging system that we built. And we have a network of recharging systems that go about 1,200 miles across the northeastern portions of the United States. A very important parameter for our customers is the recharging of the aircraft in less than 1 hour, and we target 50 minutes. Our customers are using these in the future as a tool. They aren't flying the airplane to be an airplane, they're flying it to move medical supplies, cargo, or people. So the ability for the thing to be in the air and doing those jobs is very important, and having a fast recharging time is important. Now, there are only 330 kilowatt hours of Samsung batteries in the plane presently, but in order to recharge that in 50 minutes, due to the constant current, constant voltage nature of recharging batteries, we have to supply 1 megawatt of peak power at the very beginning of charge that tailors off to very low power at the end. So this is a photograph of one of those charging systems with a elevated deck on the top. And the reason that off-airport locations have elevated decks is for approach and departure clearance requirements of approximately an 8-to-1 ratio of leaving the helipad and coming into the helipad during operations. Up here in Vermont in the United States, in the Northeast Kingdom or corner, we get a lot of snow. So the top of the helipad is de-iced. We actually heat the top of the helipad to reduce the buildup of snow and ice on the helipad. A different form of recharging for on-airport, where there are already landing zones, are these dispensers that we have deployed in the US. These dispensers have batteries tied to DC to DC converters, which are then tied to different standards. In this case, there's a CHAdeMO and a CMS charging standard. And the neat thing about this is that it can charge both aircraft and ground-based vehicles, rendering this asset more valuable to our customers. So at Beta here, we have a mission, and our mission is to bring aviation to a sustainable and clean future. When we do that, we're going to lower the cost of aviation, making it more accessible. And I believe the cleanest path to do that is to make the simplest vehicle possible. There are a lot of wonderful designs that will use thrust vectoring and liquid cooling and gearboxes, but in order to achieve certification in the near future, in the next 3 years, through the Federal Aviation Administration, we've elected to eliminate all of those complexities. So there is no liquid cooling, no thrust vectoring, no gearboxes, no complex algorithms, and simplicity, elegant simplicity for maximum reliability is really important to the design of this aircraft. The final thing I'll say is about the core values of this team at Beta Technologies and our suppliers and partners in this. We have an ethos of respecting physics. I saw some wonderful videos that the host was showing a minute ago about with flying aircraft. We have an ethos of keeping promises, and keeping promises means that we move from CAD drawings and sketches to real flying vehicles. We encourage creativity, and we know that physics and Mother Nature must be respected. Using the level of technologies that we have with batteries, motors, inverters, we can achieve something today. And that something is meaningful enough to have a commercial impact, and therefore we can use that commercial impact to create a business, and that business to lean towards a sustainable future in aviation. So thank you for having me, and I understand that there may be some questions about potentially our business or eVTOL in general.
Okay, thanks. Let's give him a
flight. So we spent many flights in hover close to the ground. And then we spent many flights on the wing on the large aircraft, and we've done hundreds of miles per flight. Those flights on the large aircraft will then come together to making the aircraft go slower and slower on the wing so that the rotors come on, and faster on the rotors, and bring the two together. In parallel, we have a whole army of small unmanned aircraft. When I say small, they're much bigger than me. And those are doing transitions every day. And those fly about 40 nautical miles, so just under 50 statute miles on their flights. And they transition from a hover to forward flight in about 15 seconds. And then they fly for about an hour. In the large aircraft, we routinely, earlier this morning, I flew for about an hour at doing stalls at 6,000 feet in the air. So the flight test program is by no means complete, but every day we go out and fly further and higher and more distance into the envelope. Presently, in the flight test program, we're moving the center of gravity further and further back and testing the stability of the aircraft. It will take another year approximately to complete all of our flight test points.
Okay, thanks.